So in Ixl level M S.3, we're going to look at graphs, try to match some exponential functions to their graphs. So a couple things to keep in mind before we start here is that we're looking at two situations. We know that these are exponential functions, but we also know that there's a big difference between exponential growth and exponential decay as far as what the numbers do and what the graph looks like. And we saw this in a hands-on way with the golf ball experiment, which was obviously an exponential decay problem. And then we saw the two examples of the Skittles activities, one of which was a growth, one was decay. But in general, if I just think about a coordinate plane here and I think about what's going to happen if I look at the graph of an exponential function, a growth function is going to be some function that is going up, is growing, and it'll grow typically pretty slowly and then really take off depending on what the multiplier is. Now, how steep this growth takes place depends on the value of A, or rather B, my fault. The function, remember from before, A times B to the X. Now, in Ixl, they love to throw K stuff at you, so let's just throw that on there. So what I mean is how steep this line is depends on how great a percentage increase we're seeing, or how big B is, basically. And A doesn't really have an effect on the steepness. A is just the starting value. But what A can do is A can cause the graph to flip. So as we saw with all the other functions we worked with this year, if the lead coefficient, in this case it's A, is negative, that causes what should look like growth to actually be decay, because the graph gets turned upside down like this. So we have to be careful, because even though you key in on this number and you see it's 2, so you think, oh, this is a function that's doubling. Keep in mind, then you're multiplying it by a negative, so it's growing but in the negative direction because of the value of A being negative. Okay, if we look over at exponential decay, and before I do that, let me just mention that, as I said before, if there is a number here, that's just going to shift the graph up or down. All right, in the case of exponential decay, these are functions in which this B value is less than 1. So, a decrease or decline in population or sales or whatever it might be. So these graphs move down. And again, if A is negative, things are going to get flipped if we have a negative A. So you have to really be careful. This right here drives growth or decay, but the sign of the lead coefficient A will flip the graph if it becomes negative, and things could be a little confusing there. So let's just look at an example. This one says, which of these graphs is the same as this function? So we just think about it. I mean, we could do the intuitive thing, which is to say, well, what would happen if I looked at the function y equals negative 2 times a third to the 0 power plus 2? Well, we know from experience that this to the 0 power is always 1. So this is negative 2 times 1, which is negative 2. And now we've got this little plus 2 part over here, which means that this thing has a value. When x is 0, y is also 0, which means it contains the ordered pair 0, 0, which means it passes through the origin. So that means these two are out. And so the question is it this one up in the upper left, or is it this one in the lower right? Well, if I look at the point, or the growth rate, it's 1/3. This means this thing is losing 67% of its value every iteration, every year, every month, every hour, whatever the situation is. So this is definitely an exponential decay problem, but I've got a negative A. So it should go down as decay does. Unfortunately, with the negative coefficient of A, it actually turns out that it causes the graph to flip. So the graph should be one that shows decay over time, but it's actually going to be turned upside down, which means that our answer is going to be this guy right here. This one's a little easier. Again, let's say what would happen. What's 3 times 3 to the 0 minus 6? That's 3 times 1 minus 6. That's 3. Take away 6. That means our y-intercept is negative 3. So we have the ordered pair 0, negative 3. Well, I see that. This one can't be. This one can't be. So I've got two choices once again. Could be, each of these has a y-intercept that looks like it's -3. And so this one up on the top here, this is a growth function, whereas this is a decay function. And so this is a situation where we're starting with 3 of something, and it's tripling every year. That's exponential growth. Without a negative coefficient, things don't get all confused, which means that's the one that represents growth. And here's one more. Let's see, y equals -4 to the 0 minus 1. That's -4 to the 0 power is the same as -4 divided by -4, which is 1. Minus 1 is 0. So again, we're going through the origin, so no and no. And this thing is a function that has a 4, which means that the a doesn't seem to be there, except you could think about this function like this. You could think of this function as -1 times 4 to the x minus 1. So even though it's quadrupling because of the 4, that basically means it's 400% of what it was each time. The graph's going to be turned upside down because of this negative coefficient. So that instead of being a really steep growth, which is what we would think, it's actually going to be this one that goes down because of that negative a value. So there you have it. Not too tough. It gets a little confusing, but if you just kind of keep the basics in mind, you should be fine. Of course, I'll give anyone who gets stuck a little help, of course, always.